Welcome back, ladies and gentlemen. This is going to be our next lesson here. What we're going to be discussing is something known as piecewise functions. Now, piecewise function is really exactly what it sounds like. It's pieces of more than one function that are being used to either evaluate a value, to evaluate something at a particular number, or graphed at the same time. But we're only looking at it over a particular portion of its function's domain. Now keep in mind, a lot of different functions have domains naturally of all real numbers. And when it comes to piecewise functions, a lot of times what we do is we restrict the domain to say, okay, we only want to look at it across this particular set of x values. And so as a result, we don't get a continuous function over the entire domain. We only get pieces of it. That's what causes it to be, that's why we call it a piecewise function, because the domain is restricted in some way that we're only looking at a certain piece of it. Okay. What we're going to look at first is simply evaluating a function for a given value. Now here we have a piecewise function, and you can see we have three different pieces. We have at the very top where it says 2x plus 3, that's a linear equation. X squared plus 1, that would be quadratic. And 5, well, that would just be a line, a horizontal line. You can think of it as a linear function as well, but it's just going to be one straight line. So we have these three pieces, two linear parts and one quadratic part. And what's on the right, where it says x is less than 0, x is greater than or equal to 0, but less than 2, and when x is greater than or equal to 2, this part over here, these are the domain. This is what we're looking at as far as the domain. These are the domain restrictions. Now, these presentations were not necessarily put together by myself. And you can see -3, -3, -3, -3. We're not going to evaluate it for -3 so many different times. So we're going to change this one to be 0. We'll change this one to be a +1, and we'll change this one to be a +2. So those are the values that we will evaluate it for those. Now we're going back to our function notation. Basically what this is saying, for function h, substitute these values into the appropriate equation to the appropriate part of the function for that number. So this is where the domain restrictions kind of come into play, at least for the evaluating part. What we're going to do is we're going to say, okay, we'll take that -3 and substitute it anywhere we can have x to be less than x to be a -3. So when we look at the domain restrictions, this one says x can be less than 0. The middle one says x has to be greater than or equal to 0, but less than 2. And in the third one, it says x has to be greater than or equal to a +2. So in this case, because -3 is less than 0, that says substitute it into the first equation, 2x plus 3. So I would get 2 times -3 plus 3, and that will give me -6 plus 3, which ultimately is just a -3. So h of -3 is equal to -3. And so we're going to use the same approach for the remaining 4. Again, -3 over 2. Well, where does it fit in these three domain restrictions? -3 over 2 is still less than 0. So because it's less than 0, it'll still go into the first domain. Because it's less than 0, it's got to go into that first equation, because that's the only piece, that's the only function that allows me to use something that is less than 0. So here, because -3 over 2 is still less than 0, that says stick it into that first equation. So I would say 2 times -3 over 2 plus 3. Here the 2's simplify, so I have -3 plus 3, which gives me 0. So h of -3 over 2 is equal to 0. So now let's take a look when x is 0, the next one in the list. So here, x is going to actually equal 0. Now, if you look at the domain restrictions, the first one says x has to be less than 0. It cannot be equal to 0. The middle one says x can be greater than or equal to 0. So since 0 is greater than or equal to 0 and it's less than 2, that tells you that it's going to go into that second part. So we're going to say x squared plus 1 and just substitute 0 into it. So 0 squared plus 1 is just 1. So h of 0 is equal to 1. Now looking at the next one, h of 1. 1 also is less than 2, but it is greater than or equal to 0. So that tells you it also goes into the quadratic portion of the piecewise function. So substitute the number into the x squared plus 1 part of the piecewise, and I'm going to get 1 squared plus 1. Well, that's just going to give me 2. So h of 1 is equal to 2. And the last one. Here we have h of 2. So because the value is exactly 2, well, we can't put it into the middle expression because it says x has to be less than 2 in the middle expression. But in the third one, where we just have the part that's 5, that one has a domain saying that x is greater than or equal to 2. So since 2 is greater than or equal to 2, that goes into the third expression, which is just 5. So because, well, let me write that a little bit more properly. Because there are no variables to substitute into it, because it's just 5, anything that is going to be that is going to be 2 or greater is always going to produce the number 5, because that would just be like a horizontal line on a graph. So here we will say h of 2, well, that would just be 5. And because anything 2 or greater is only going to be able to produce a 5, because there's no other math to do. There's no x values to substitute or anything. And so this is pretty much what we're going to do. All you have to do is see for our input numbers, whatever they happen to be, where are they allowed according to the domain, of whatever those restrictions happen to be. And once I see where it belongs, we just substitute into it and evaluate it and see what we get. So now we have an actual piecewise function that we're going to graph. And this is typically how we see it. We see function f on the left, and it's equal to, and we have a big curly bracket where we have both parts, or in this case both parts, of a piecewise function. So the top part, 1/2 x plus 1, that's a linear expression. And we have a domain restriction for that one saying that x has to be less than or equal to 0. The second part of the piecewise function says x minus 2 to the second power minus 3. So because we have something squared, that tells you it's a quadratic function. And we're leaving it kind of in, in this form so we can see, in vertex form, so we can see kind of how the transformations are occurring. Now, this one is also giving us a domain restriction where we're saying x has to be greater than 0 and it has to be less than or equal to 5. Now, the reason why I have two graphs here is because I think it'll be easier to see how we would graph it normally and along with how we would graph it as a piecewise function. So let's take a look at the first equation, 1/2 x plus 1. Well, the y-intercept is a positive 1. So here's the origin. So positive 1 is right here. So a slope of 1/2, positive, says it's going to go up to the right one space. I'm going to go up 1 and to the right 2 times. Up 1 and to the right 2 times. Or I could go down 1 to the left 2 times. And what we're going to wind up with is a continuous graph that uses all real numbers for the domain, and it looks something like that. Now, what is different about this versus a normal function is that here we really have to look at, well, what is this domain telling us? These are the only numbers that we can use. So this is what the graph would look like. That solid line, that's what it would look like normally with no restrictions on it. But now we're looking, okay, well, we have a restriction. So here it says x has to be less than or equal to 0. Well, because of the type of inequality, because it has the equal to part, that uses a solid dot instead of a circle. And because we can only use the stuff that is 0 or less, that means everything to the right here is gone. We can't use it anymore. And so what we're left with now, that is the piece of the piecewise function that we can actually use. So that's what it would so we started off with what it would normally look like. And we've gone to, well, this is the only part that we can actually use because that's what the domain restriction is. So on the graph on the right, I'm going to just go ahead and put what we're actually allowed to use. So we're at 0. And from here, we would just have a continuous function like that. And of course, this is a closed dot. So now let's take a look at the quadratic one. And let's do a different color for that one. Here, the stuff in the parentheses, the x minus 2, remember the stuff in the parentheses, that's going to affect some horizontal something or other. So in this case, we're going to translate the quadratic parent function 2 spaces to the right, and the minus 3 says we're going to translate the parent function 3 spaces down. So from the origin where we would normally start, the quadratic parent function, we're going to go 2 spaces to the right and 3 spaces down. So right here is where the vertex would normally be. Now for the quadratic parent function, since there's no transformation as far as like a vertical stretch or a vertical compression, there's no number in front of the parentheses that would cause us to do that. The rest of the function is going to look exactly like the quadratic parent function, except it's been translated 2 spaces to the right and 3 spaces down. So from the vertex, if I went to the right one, meaning that, like if we said x was 1, we would go up 1. And of course, because it's a parabolic shape, everything that I do to one side, I do the same thing to the other side. So from the parent function, if x was 2, y would be 4, meaning I would go up 4 spaces. So I would have a point here, and I would have a point here. If x was 3 from the parent function, 1, 2, 3, well, y would be 9, because 3 squared is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So let's see, 1, 2, 3, 1, 2, 3. So and let me see if I can get this on here without messing up my points too bad. The transformed parabola would be something like that. Well, now let's take a look at its domain restrictions. Its domain restriction says it has to be greater than 0, but less than or equal to a positive 5. So let's take off everything that is less than 0 and anything that is greater than or less than or equal to a positive 5. So the inequality for the 0 says that we would have an open circle there. And the inequality for the 5 says that we would have a closed dot there. So this is what the parabola would look like with the domain restrictions applied to it, saying that x has to be greater than 0 but less than or equal to a 5. So this is what would also be graphed with the linear portion over here. So at the vertex 2, negative 3, let me go ahead and put that in. There's the vertex, so I would have an open circle here. Now, because I have an open circle there for the quadratic, but a closed circle for the linear function, it's still included for the overall part for the overall function. And Now we're going to just plot the rest of our points. So we have, where are we at? 4 and 1 is a point, and 5 and 6 is where we stopped. So we're going to go from here down and up, and then we stop. It's not continuous anymore. So it's continuous to the left because we're saying x is less than or equal to 0. But because it's less for the quadratic, because it's less than or equal to 5, well, we can't be greater than 5, so we have to stop right there. And so both of these together is what the final graphed solution would be for this particular uh, piecewise function. So now we're going to bump it up a little bit. We're going to give you 3 functions to try and graph at the same time as opposed to 2. And this is really about the most complicated as it will get. We could get more. We could do 4 or 5 or whatever, but they just become ridiculously complicated at that point, and we're not going to try bothering with it. So we're going to have these 3 functions that we're going to graph. And again, we're going to try and do them a piece at a time. So I'll graph the original function that it would have on the left, identify what the domain restrictions would be, and then we'll transfer that to the graph on the right. So let's look at the linear function, -1/2 x minus 1. Well, here's the origin. So the y-intercept is at a -1. The slope is -1/2. So I would go down 1 and to the right 2 times and plot some points, or upright and to the left 2 times and plot some points. So the normal function would look something like that. Now let's see what the domain restrictions are. The domain restrictions say that x has to be less than -3. So right here at -3, I'm going to put a circle around that because that's what the inequality symbol says we're using. And since x is going to be less than -3, everything to the right of that is going to be gone. So that's the only piece that we really have for the linear part of the piecewise function. So let's go ahead and transfer that over here to the graph on the right. So at -3, we're about right here, and then we have a point here over 2, over 1 up to, I don't know why I'm having a hard time wanting to graph this right now. So let's see. Here I have a point up 1 over 2, up 1 over 2, so we would go like that. And it is continuous because it says it is less than -3. Okay? And so now let's go ahead and go to the next portion. Let me clear this off so we can have a clean graph to work with. So now let's look at the absolute value graph. This one has 2 transformations. The negative in front of the absolute value symbol says it is reflected across the x-axis. And the +5 says that it has been translated up 5 spaces. So since I'm not doing any horizontal transformations of any kind, my vertex is going to be right there at a +5 since we translated the parent function up 5 spaces. The negative in front of it says that, well, now it's reflected over the x-axis. So instead of opening up like a V, now it's going to open down. And the parent function itself basically has a slope of 1 on either side of the vertex. So it would kind of open down looking like that. So now let's see what are the domain restrictions. So x has to be greater than or equal to -3. So I'm going to go to -3, and I'm going to put a dot right there. And then I'm going to go to a +5, and because of that inequality symbol at +5, again, I'm going to put a dot. And so everything else on either side of those dots we can't use because they're outside of the domain according to the piecewise function. And this is what we wind up with left as what we can use. So I have a point at +5. I have a point at -3 and +2. 2, so I have a point right here. And then I have a point at 5 and 0, so I have a point right here. So this is what we wind up with as part of the for the absolute value portion of it. And let me pick another color here so we can keep differentiating. And let's just do blue for the radical one. And let me go ahead and clear off this so we can have a fresh start. Now, what we see here is, again, two transformations. The stuff underneath the radical symbol says we're going to translate the parent function 5 spaces to the right, and the 3 in front of it says we're going to stretch it vertically by a factor of 3. So the parent function normally starts at the origin. Well, we're shifting it 5 spaces to the right, so now we're going to start here at the 5. Now, the parent function says that, like, when x is 1, the square root of 1 is just 1, so I should go to the right 1 and up once. But that 3 says we're stretching it by a factor of 3. So instead of going to the right once and up once, I'm going to go to the right once and up 3 times. If I went to the right 4 times, normally on the parent function I would go up 2 times. But here if I go to the right 4 times, because I'm going up 3 times as much, well, 3 times 2 would be 6. So 1, 2, 3, 4, 5, 6. So that's about all we're going to be able to fit on here, and we're saying x is greater than that, so it's continuous to the right. So let's go ahead and plot those points here. At 5 and 0, we have a point, close dot. At 6 and 3, we have another point. And at about 9 and 6, we have our last point. So we have something that goes like that. Now I want to point out something to you right here. This gap says that this piecewise function is discontinuous. A discontinuous piecewise function, imagine if you traced this out with your pencil. You would have, like if you started at the far left, somewhere about here, and you trace that red line down to where that dot is, at some point you have to pick your pencil up to move it to that new dot where the purple absolute value function starts. Because we have to pick our pencil up, if we were to try and trace this, because we would have to pick our pencil up and jump that gap, that would be known as a discontinuous piecewise function. Where if you looked back at this original one, if we did the same thing, if we traced this one out, we would not have to pick our pencil up to cover the whole thing. So this one would be known as a continuous piecewise function. Now, that's all the examples that we're going to show you for this lesson because they are a little time consuming to try and demonstrate. We'll work some more in class probably together, but for the time being, I want to just get you started with those. If you have any questions, please make sure you come to class with what you need help with, and we'll see you again soon.